Examples of Newton's second law. Here's the diagram of the problem outlined here. We have two boxes sitting side by side on the floor. I didn't draw the floor. It's not important. What's important are the two boxes. And there's a 10 Newton force applied to the box from the side horizontally. And there's no friction with the floor. Part A, draw a free body diagram of each box. So we'll draw each box by themselves. So here's the 3 kilogram box. It has the force of gravity straight down. Now in this case I'm going to actually calculate that. We call that the weight of the box, the force of gravity. And as we've seen in class, the equation is W equals mg to find the weight. And I'm going to do some rounding here. The weight of that box is the mass, 3 times g, which is 9.8, or if you want to use 10 for g, the acceleration due to gravity, the weight of that box is 30 newtons. Slightly under that if you use the 9.8, but let's just use the rounded off version, 30 newtons. That's the force of gravity. Now, since the box is sitting on the floor exerts an upward force. Now in this case, which is the case in a lot of situations, the upward support force when you're standing on something is exact opposite but the same numerical magnitude as the downward force, 30 newtons. So those two forces, the net force of those two forces is 0. Those aren't going to cause any motion. But what's going to cause motion is the sideways force that's applied by maybe it's a person pushing, doesn't really matter, but there's a sideways force of 10 newtons on that box. And then anything else that touches that box, which is box B. Now here's where it gets a little bit tricky. There's another force on this box. And the other force on this box is to the left. That's the resistance it feels from box B, or it's the force of box B on box A. I can label that a lot of different ways, but one way to do that is force B dash A. That means the force that box B exerts on box A. Force B dash A, subscript there. Those are all the forces acting on the little box. Now the big box is 5 kilograms. Trying it a little bit too large, but that's okay. 5 kilograms. It also has a downward force of gravity, weight. And since we're using rounded off numbers, you can just label that as 50 newtons, because it's going to be 5 times 10 of 50 newtons. And as what happens most of the time when you you run on a level surface, the upward support force from the floor will be 50 newtons. Those two forces will cancel out. However, box B is not being pushed by the 10 Newton force, it's being pushed by box A. So the way I can label that is F A dash B. What that means is the force that A exerts on box B. That middle pair there, where I have F B dash A and F A dash B, is a good example of Newton's third law. For every action, there's an equal and opposite reaction. Box A pushes on box B pushes back on box A. Whatever that number is, 6 newtons, 8 newtons, it's the same for both boxes, but opposite direction. And one of our jobs will be to figure out what that force is. So there we go. We have the free body diagrams. Now we have to do part B. I'm first going to do this problem the hard way. Then I'll show you a little trick or the easy way to do the problem. But what we're going to be using is Newton's second law, and that is F net equals ma. We're going to apply the F net equals ma, the second law, to each box. So F net 1 is mass 1 times acceleration number 1. F net 2, second box, or I should call it box A and B, I guess. 1 and 2, A and B. Mass 2, acceleration 2. So here's how it works. On this first box, the little box, the net force is always the big force minus the small force. Now these boxes will accelerate to the right. So I know that the force in between the two boxes, the interaction force between the two boxes, is smaller than 10 newtons, because let's look at the little box, it's going to accelerate to the right. So what you always do is you take the big force minus the small force. I'm just going to call it F now. I'm going to leave off this subscript BA, because it turns out, as we know from Newton's third law, FBA is the same size numerically as FAB. So I don't need those subscripts, but mass number 1 is 3 kilograms, and I also don't need the subscript for A sub 1 because they both have the same acceleration. A1 and A2 are the same. They are moving as a system, so I have 10 minus F equals 3 times A for the little box. For the big box, the net force, there's only one force, there's no friction, so it's just F equals 5 times A. Well, we have a system here now. We have these two equations that have an F and an A. So I'm just going to use substitution. I'm going to substitute the 5A in for the F over here, and it results in 10 minus 5A equals 3A. If you solve that for A, you get 10 equals 8A, or A equals be 10 divided by 8, which is 1.25 meters per second squared. Now that I have the acceleration of the boxes, actually that's the acceleration of both boxes, they accelerate together. That's the answer to part B of the problem. The acceleration of each box is that value, and everything else falls in very quickly now. For example, I can go to either one of my equations at the top here now. Let me just circle them. Let's say I'll just go to this one. And if I just plug in for A, I get F equals 5 times 1.25. F comes out to be, I believe that is 6.25 newtons. Right, so that's the answer to part C of the problem. That's the force that each box is exerting on each other. The little box pushes on the big box with that force, the big box pushes back on the little box. That's the interaction force between the two boxes, FBA, FAB. Same force, equal and opposite on each box. Now the net force on box A, and I only have space over here to the left now. I'll use black again. So for part D, I want the net force on box A. Well, the net force on box A is going to be the big force minus the small force. The pushing force is 10 newtons. Minus the resistance force of 6.25. So the net force on box A is 3.75 newtons. That's to the left. I'm sorry, to the right. That's the net force is to the right. And then for box E, the net force is the only force acting to the right. The up and down forces are all canceling. So those don't contribute to the net force. So in box E, just observe, it's 6.25. F net is the 6.25 newtons. That is the net force on box B. All right, here's a little technique that could be a time saver. If you treat the two boxes as one box, a system of 8 kilograms, because 5 plus 3 kilograms is 8 kilograms, and then a 10 Newton force pushing on this one system, that 10 Newton force is blind. It doesn't really know whether it's pushing one box, two boxes, 8 boxes, or 10 boxes. It just kind of feels that there's an 8 kilogram mass it's pushing. Now, once again, there's a weight of 80 newtons, because the weight is the mass times 10. So it's an 80 Newton force of gravity. There's an 80 Newton force of support. These two forces really aren't that important, but we should draw them because that's the free body force diagram of the system. But the only thing that causes acceleration is that 10 Newton force. And we're going to apply Newton's second law. Once again, F net equals ma. Well, the net force on this system is just the 10 newtons. One force, it's the net force, equals the mass, which is 8 kilograms, times the acceleration of the system. And if you do the math here, you get 8, lo and behold, equals 1.25 meters per second squared. Same answer as before. So that's a fast way to get the acceleration of the system. And then you can go back and break the system apart into two boxes like we did before.